Have you ever looked up at the sky and wondered why the sun, a gigantic nuclear furnace, doesn't just explode? It's a fair question. Every single second, our sun releases as much energy as 16,000 tons of TNT. And yet, it's been shining steadily for 4.6 billion years. So, what's stopping it from blowing up like a colossal hydrogen bomb? The answer lies in a beautiful cosmic balance, powered by three key mechanisms: controlled nuclear fusion, gravity, and a brilliant self-regulation system. Let's dive in. First up, the engine of the sun, nuclear fusion. The sun isn't burning like a log in a fireplace. Instead, deep in its core, the conditions are absolutely extreme. Temperatures hit 10 million degrees Celsius, and the pressure is 250 billion times that of Earth's atmosphere. In this inferno, hydrogen atoms are squeezed so tightly that they fuse together to form helium, releasing a tremendous amount of energy in the process. But here's the crucial difference between the sun and a hydrogen bomb. A bomb creates an uncontrolled chain reaction that happens everywhere at once. The sun's fusion, however, is a much more civilized affair. It happens only in its small, tightly confined core, and the rate of this fusion naturally regulates itself. It's like a perfectly managed power plant. The sun consumes about 4.5 million tons of hydrogen every second, which sounds like a lot, but it has enough fuel to keep shining for another 5 billion years. Right now, it's only about halfway through its life, basically a middle-aged star. So, if fusion is constantly pushing outward, what keeps the sun from flying apart? That's where gravity comes in. The sun's enormous mass, about 330,000 times that of Earth, creates an immense gravitational pull. This gravity is constantly trying to crush the sun inward, compressing its core and providing the exact pressure needed for fusion to happen in the first place. This creates a perfect cosmic tug-of-war, a state scientists call hydrostatic equilibrium. Gravity pulls in, and the radiation pressure from fusion pushes out. These two opposing forces are so precisely balanced that the sun maintains its stable spherical shape and its consistent brightness. It's a dance of cosmic proportions. There's also another amazing safeguard built into this system: a photon of energy. A particle of light created in the sun's core doesn't just shoot straight out. It bounces around inside the sun for hundreds of thousands of years before it finally reaches the surface. This incredibly long journey acts as a massive buffer, preventing any sudden surges of energy from reaching the outside and disrupting the balance. Now for the third, and perhaps the cleverest part, the sun's dynamic self-regulation system. The sun isn't just a silent, static ball of gas. It's alive with motion, magnetism, and constant adjustments that keep it stable. Its outer atmosphere, the corona, reaches a scorching 1 million degrees, releasing a continuous stream of energized particles called the solar wind. This wind carries away about 1 million tons of material from the sun each year. That sounds like a lot, but it's a tiny fraction of the sun's total mass, like a person losing a single eyelash. At the same time, hydrogen from the sun's outer layers is constantly, slowly drifting inward, replenishing the fuel supply in the core. This continuous circulation helps keep the sun's internal fuel distribution balanced, ensuring a steady energy output. Then you have the dramatic stuff: solar flares and prominences. The sun's magnetic fields are constantly twisting, folding, and storing up enormous amounts of energy. When these magnetic field lines suddenly snap and reconnect, we get spectacular eruptions that blast energy into space. These events might look violent, but they actually act like pressure release valves, safely venting excess energy and protecting the sun's overall stability rather than threatening it. And here's the truly brilliant part of the self-regulation system: a fast-acting feedback loop. Imagine the sun's core gets slightly compressed by gravity. The pressure and temperature increase, which speeds up the rate of fusion. This, in turn, creates more outward radiation pressure, causing the core to expand back to its original size. Now, what if the core expands a little too much? The pressure and temperature drop, slowing down the fusion rate. With less outward push from fusion, gravity takes over and pulls the core back inward, restoring the balance. This elegant feedback loop happens constantly, keeping the fusion rate incredibly stable and preventing both a runaway explosion and a catastrophic collapse. So, will the sun shine forever? Sadly, no star lives forever. In about 5 billion years, the sun will finally run out of hydrogen fuel in its core. When that happens, the beautiful hydrostatic equilibrium will break. Without the outward push of fusion, gravity will win the tug of war, and the core will start to contract and heat up. This will trigger a new phase. The sun's outer layers will expand dramatically, swelling to over 200 times its current size. It will become a red giant, large enough to swallow Mercury, Venus, and quite possibly Earth. After about 1 billion years as a red giant, the sun will shed its outer layers, creating a beautiful, glowing cloud of gas and dust called a planetary nebula. All that will be left behind is its hot, dense core, a white dwarf. This Earth-sized remnant will no longer have any fusion happening inside it. It will simply shine with leftover heat, like a glowing ember from a colossal fire. Over tens of billions of years, it will continue to cool down, eventually fading into a cold, dark black dwarf, the final cinder of our once mighty star. So the next time you feel the warmth of sunlight on your skin, take a moment to appreciate the incredible cosmic balance that makes it possible. It's a delicate dance between fusion, gravity, and magnetic forces that has kept our star shining calmly for billions of years. And just like everything else in the universe, our sun has a beginning, a middle, and an end.